guys, welcome to Kisscrew Chemistry Help, where we take chemistry to the concrete so that you can succeed. Today I want to teach you a technique called serial dilutions, and it's actually pretty cool because it saves a lot of time, money, and material. And it's an essential skill that you'll need if you're going into any of the biomedical professions, genetics, biology, biochemistry, PhD research, engineering, nursing, and after all, maybe chemistry. So without further ado, let me teach you this concept. Alright, so let's get into it. First of all, what are serial dilutions? It's actually a method of making increasingly dilute solutions from one stock solution. So the application for this, you can use serial dilutions to determine the antibody load in biomedical applications. So finding the lowest level at which an antibody is produced in response to the presence of an antigen. Now the other way that serial dilutions are relevant is pretty much in any situation where you have to make a more dilute solution from a more concentrated solution. It's depending on what kind of glassware you have access to, it's a way to save time and material and money because you are not spending as much money on materials, you're not wasting as much solvent to create the solutions because you have smaller glassware at the ready. So this could be useful for virtually any chemistry lab experiment that involves solutions. So an advantage is that it indeed saves time and material, but a disadvantage of serial dilutions is that if you execute making any of the solutions or calculating any of the solutions incorrectly, then all of the following solutions after the point where you deviated will be wrong. So now let's talk about the math associated with serial dilutions. So first of all, you have to start by determining the concentration of your stock solution. Ask yourself the question, how many grams will I actually need to deliver to solve the problem or to observe the experiment? Does the problem give a molarity? The other question you could ask is, if you're working on a homework problem that's a paper and pen problem, then you also might ask yourself if the problem gives a molarity, and if so, if the problem is giving you a molarity, then you are already ahead of step from where I'm going to be talking about, so that's kind of good. The calculation will be working backwards from molarity to find the grams that you need to add to the volumetric flask in order to actually create the solution. Now in our example that I'm going to be showing you is actually, we're creating solutions that will actually be used in the acid rain pH shifting experiment that has to do with my trip to Chicago. And if you'd like to see that, you can go ahead and click this link up here and a link to it. Perhaps you're even coming from that video to learn more about how I made the serial dilutions to actually show the pH changes. In our example, we wanted to make 4 solutions, one increasingly dilute from the next, and we wanted to start with a molarity of 0.1 molar sodium hydroxide. So that means that our stock solution, the very first one we're dealing with, is going to be 0.1 molar sodium hydroxide, and then we wanted tenfold dilutions after that. Now you could put any number in for the factor of dilution. I'm just drawing an X because it's like 10 times dilution, but you could put any number there. It just so happens that in our case we wanted to do tenfold dilutions 3 times to make 4 total solutions. So in essence we're making a 0.1 molar solution, a 0.01 molar solution, a 0.001 molar solution, and then a 0.0001 molar solution of sodium hydroxide. And actually, if you want to learn more about scientific notation, because that is a lot of O's, click the link up here. I will try to put a card in so that you can actually see that video as well. And it might take me a little while, but I will get there. Here's the math associated with it. If we know we have a 0.1 molar stock solution, then we want to figure out how many grams we need to put in the flask so that we can actually make that 0.1 molar solution. So we'll start with 0.1 moles per 1 liter, because that's the definition of molarity, is number of moles per liter. And then we're multiplying by the molar mass of the chemical. In the case of sodium hydroxide, it's 23 plus 16 plus 1, which is 40 grams per mole. So for every 1 mole of sodium hydroxide, you have 40 grams. And then multiplying those two together, you cancel your units of moles and you wind up getting grams per liter. So in that liter, that's the number of grams of the chemical that you're going to put in the flask. And now you want to also find, if this is the number of grams we want per liter, then we're going to need to find how many grams that translates to in 50 milliliters. So in that case, we would actually multiply by another factor of 1 liter per 1,000 milliliters, and then multiply again by 50 milliliters because the total volume of the volumetric flask is 50 milliliters. And that's unique to our situation because the only volumetric flasks I own are 50 milliliter volumetric flasks. So that's the volume that we're targeting to work with. Now, once you've figured out how many grams go in the 50 milliliter volumetric flask, you'll weigh it out on the balance. You'll put that sample, once it's weighed, into the volumetric flask, and then you will fill to the line with a solvent. In this case, we're making a 0.1 molar sodium hydroxide aqueous solution, meaning it's being dissolved in water. So we'll fill the volumetric flask to the line with water. Now, the essential equation that you're going to know for this is M1 V1 equals M2 V2. Now, what does this mean? Because that's a lot of M's and a lot of V's and my head's already spinning. Well, the units for M is molarity, meaning moles per 1 liter. The volume is in units of milliliters, but it also kind of doesn't matter because the volume units will cancel since they're on both sides of the equation. But for right now, let's think about it in terms of milliliters because that's something very easy and concrete to understand. Now, here are some definitions of what the 1 subscripts and the 2 subscripts mean in this context. M1 is the molarity of the solution that you're pulling from. So your stock solution, in the case of when we make the second solution, you're going to pull from your stock solution. In the case of making the third solution, you're going to pull from your second solution. So M1 will be the second solution molarity, and so on. And then V1 is the volume of the solution that you're pulling from. So that's usually X in the problem because we don't really know how much we need in order to dilute to get the second or third or fourth solution. So that's what we're going to solve for. And then M2 is the molarity of the solution that you're creating, and we know that it's going to be a tenfold dilution, so if we started with 0.1 molar, we're going to make a solution where M2 is 0.01 molar. And then V2 is the volume of the solution you're creating, so we know we're making a solution of 50 milliliters. And then, so to reiterate, when we're making our solutions, we're usually solving for volume 1, V1, so that we know what fraction of the first solution we need to take to put into the second solution so that we can dilute it to the right level. So in our example, when we plug in our numbers of 0.1 molar times X milliliters equals 0.01 molar times 50 milliliters, we can solve for X and find that we need 5 milliliters of the 0.1 molar solution to add to the new flask, and then we fill to the top line of the volumetric flask with 45 milliliters of solvent. Now, it may not be exactly 45 milliliters because solvent is a little bit compressible, but the idea is that we fill it to the line and it should be adequately our 50 milliliter solution. We continue with this process when we solve for X, plugging in the second solution molarity and the third solution molarity, knowing that all of our volumetric flasks are at 50 milliliters large. Then we solve for X and find that it's also 5 milliliters, and so we add the solvent to the line. Now, this makes sense that we would have the same 5 milliliters to distribute from the second solution to the third solution, from the third solution to the fourth solution, and so on, because we're making tenfold dilutions. So if every solution is diluted tenfold from the previous solution, then that means that we would expect the same volume from the previous solution to be added to the next solution. And here's a diagram showing that process. After we've made our stock solution, we take the volumetric pipette and we pull up 5 milliliters into the volumetric pipette, and I'm going to demonstrate this with our demo. And then we would distribute it into the second volumetric flask, so we release that volume and it goes into the flask. Then we fill the second flask to the line, and then we will shake it to distribute it evenly throughout the solution, and then we will take that volumetric pipette again and we will pull up and then distribute the 5 milliliters to the next flask, and so on until we've reached the 4 solutions that we wanted to make. So now let's go into the demo, and I'm going to show you more. Alright guys, so this is the video for today. Serial dilutions, a great technique for any biomedical applications and even any chemistry applications. If you liked what you saw today, please like and subscribe to my channel. I put up new content about every other Thursday, and hit the notifications bell so you can be tuned into our live chats and our premieres every Thursday at 7 p.m. Eastern Time. If you also are looking for any school supplies, modeling kits, or textbooks, I urge you to check the down bar because I have links there, and I do make a small affiliate commission off of that, but I do personally recommend these types of school supplies and modeling kits because they stimulate learning and engagement. So thank you so much for your time, and I look forward to seeing you next week. Bye guys!